For the isobaric process, in other words, the constant pressure, then in that case, with a constant pressure, we can say that the work done by the gas is just P delta V. So, let's keep in mind, this only works for a constant pressure, okay? So that P is a constant value. Well, in that case, we have W is P delta V, so delta U is Q minus P delta V. And here we have the relationship of the first law of thermodynamics for an isobaric or constant pressure process. What about the isochoric process? For the isochoric process, we've got a constant volume. Now, if the volume of the gas is held fixed, in other words, we do not allow the piston to move, then the gas cannot do any work. There is no work done by the gas. If there's no work done by the gas, then delta U, which is Q minus W, and if W is 0, then the only way to change the energy of the gas is by adding heat. Keeping the piston clamped in place does not allow the gas to do any work, nor to have work done on the gas, so the only way to change the internal energy of the gas is by adding heat or removing heat from it. Okay? What about the isothermal process? For an isothermal or constant temperature process, we cannot say that W equals P delta V, because P is not constant anymore. The pressure changes for an isothermal process. So we have to write this as an infinitesimal change. dW, the infinitesimal amount of work done, is the pressure times dV, the infinitesimal change in volume. So the total amount of work done is the integral of dW. But what's dW? dW is P dV. P, from the ideal gas law, we know PV equals NKT, so P is NKT over V. The integral of dW is then, because it's isothermal and the temperature is constant, we can pull the NKT out of the integral, so we'll have the total work done is NKT times the integral of dV over V. But what's the integral of dV over V? That's log V. If we integrate this from the initial to the final volume, V1 to V2, it'll be NKT log of V2 minus log of V1, but the difference of logs is just the log of the ratio, so this is NKT log V2 over V1. But there's something else. We know that delta U equals Q minus W, and delta U is 3 halves, whoops, forgot the 3 halves, 3 halves, NK delta T. But at constant temperature, what's delta T? Delta T is 0. If the temperature is constant, T is not changing. Delta T is 0, so that means delta U must be 0. Q minus W is 0. Q equals W. So not only does this equal the total work done, this must equal Q, the heat added to the system. Very, very interesting. So this gives us a very, very interesting result for an isothermal process. It tells us the amount of heat added to the system related to the change in the volume. Okay, very good. There's one more process I want to talk about. These were the only 3 that we looked at before, but there's one more that I want us to consider. I just realized that I forgot to change the numbers here for the different processes. So we're up to number 4 here. And this is the adiabatic process that I want to talk about. Let's go back to the first law of thermodynamics. We've got delta U equals Q minus W. We looked at the isobaric process where the pressure was held constant and the work done had a very simple form, P delta V. But then, the isochoric process, where the volume was constant, the work done was 0, and so we just had delta U is equal to Q. We looked at the isothermal process, and that was where delta U was equal to 0, and we ended up with just Q equal to W. So we've looked at W equals 0, delta U equals 0. What if Q equals 0? In other words, what if there's no heat added to the system nor taken from the system? Well, that's what the adiabatic process is. The adiabatic process means that Q is equal to 0. No heat is added to the system, nor taken from the system. So if this is 0, what do we have? We have delta U is equal to minus W. But delta U, we know, is equal to 3/2, this is for the ideal gas, 3/2 NK delta T. So if minus W is equal to that, then we know that the work done is negative 3/2 NK delta T, or the work done is 3/2 NK. If delta T is T final minus T initial, negative of that will be T initial minus T final. And there we have a very simple result for the work done. The work done by the gas is directly related to the change in the temperature of the gas. Very good. There's one more thing I want to add about the adiabatic process. I won't derive this, but it's derived in the book. And that is, what's the relationship between, we've got this in terms of the temperature. We know the temperature is, this relationship tells us what the work is. We know the work is related to the pressure and the volume somehow. Well, it turns out for an adiabatic process, the pressure times the volume, we know for an isothermal process, PV equals a constant, but for an adiabatic process, with the temperature changing, PV to the gamma is equal to a constant. And for an ideal gas, this constant gamma, which is related to the heat capacity of the material, heat capacity at constant pressure and heat capacity at constant volume, for an ideal gas, this is actually 5/3. So that's a very nice relationship that can be used for an ideal gas, and it relates the pressure and the volume for an adiabatic process. Very, very good. Okay, let's move on to the second law of thermodynamics. The second law of thermodynamics states that heat flows spontaneously from a substance at a higher temperature to a substance at a lower temperature, and does not flow spontaneously in the reverse direction. Well, this seems like something that's very common sense. You take a hot object and you put it in contact with a cold object. Heat from the hot object will go into the cold object. The hot object will cool down. The cool object will warm up. But this law states that that has to happen, or that does happen. This is actually a very different kind of law. It says it flows spontaneously. Why does it do that? The reason that heat flows from hot to cold is because it is the most probable thing to do. For heat to go from a cold object to a hot object is extremely improbable. Let's take a look at that for just a minute. The second law is telling us that if we have a hot object in thermal contact with a cold object, heat is going to spontaneously go from the hot object into the cold object until we reach thermal equilibrium, and then basically both of them will end up, just say some equal temperature in between. Depending on how hot, maybe they both end up hot, but just not as hot as they were before. But I think you get the idea. So heat is going to go from the hot object to the cold object. Why can't it happen that if we put two warm objects together, why doesn't heat go from one to the other and we end up with this situation? Because it is too improbable for something like that to happen. Let me give you an analogy that might give you a better idea of what we're talking about. Let's imagine that we have a container that's got a divider in the middle. And we put 1 mole of gas over on one side, so we've got 1 mole of all these particles over here that are all flying around in random directions, and there are no particles over here. So we start with everything here, nothing there. But then, let's imagine we open up a little doorway in between. What's going to happen? Well, because the particles, we're assuming it's an ideal gas, don't interact with each other, every particle is free to move on its own, but anytime one of these particles happens to come over and go through the doorway, it's now going to end up over this side. Because there are so many particles over here, 6.02 times 10 to the 23rd, a whole bunch of them will be coming over here and passing through this doorway, and we'll start to get some particles over here. However, these are going to be moving around over here. There's nothing stopping one of those from coming back over this way. However, because there are so many here, and initially at least there are fewer here, we're going to end up with more particles going that way and fewer particles coming this way. And we will keep having more particles going that way than this way until we basically have the same number of particles over here as we have over here. In other words, a half mole over here and a half mole over here. When we have equal particle numbers, then we'll have just as many going that way as we have this way, and we'll basically be in equilibrium. But would it be impossible for more particles to just by chance randomly come over here and end up over here? Could we start with a half mole here, a half mole here, if we waited long enough and just waited for enough particles to come over this way but not go to that way? Could we end up with none over here and a whole mole over here? Well, let's think about this as a probability issue. Let's imagine we have one particle What's the probability of finding one particle over on the left side? Well, it'll be 1/2. So the probability for one particle will be 1/2. What if we have two particles? Let's say like A and B. We could have A and B over here, A here, B here, A here, B here, or both particles over here. So we've got a chance of 1/2 of finding one over here, a chance of 1/2 of finding one over here, the other one, and 1 out of 4 of finding both. So the probability of finding both on the left side is 1/2 times 1/2, which is 1/4. What if we have three particles? Well, what's the chance of finding the third particle over here? Well, again, it's another factor of 1/2, so it would be 1/2 times 1/2 times 1/2. Okay, 4 particles, another factor of 1/2, 5 particles, another factor of 1/2. A mole of particles, well, it will be 1/2 to the power of 6.02 times 10 to the 23rd. Well, that is a very, very small number. Bringing this up on top and changing this to base 10, this would be like 10 to the negative 1.81 times 10 to the 23rd. In other words, 0.0000 with 1.81 times 10 to the 23rd zeros before we come to a non-zero digit. Well, that is extremely, extremely improbable. Is it impossible? Well, I wouldn't wait for it to happen if I were you. We can definitely define what the probability is, but that's not going to happen. So the reason that the particles end up evenly distributed, or at least fairly evenly distributed, we don't mean exactly 1/2 and exactly 1/2, but something around 1/2, and the probabilities can be determined. If you've got more energy over here, it is much, much, much more likely for that energy to go over to a region where there's less energy, more probable than having the region where there's less energy sending energy over to the region where there's more energy. Okay, so the second law of thermodynamics is basically telling us what's much, much, much more probable, and it's much more probable for heat to flow naturally from a hot object into a cold object than to have it go the other way around. Okay, very, very good.